In the question, you are given two planes, right? A linear equation, the graph of a linear equation of three unknowns is a plane. You imagine you have two planes in the space. In this case, the two planes are not parallel. The two planes are not parallel, right? So because the first plane has the first plane, that plane, I mean, the underlined plane has a normal vector of now let's say three components are coming from the coefficients of x, y, and z. Okay, the first plane can use n1 to denote the a normal vector of that plane. I told you last time the first plane has a normal vector 2 is coming from the coefficient of x, and then 1 is the coefficient of y, and the negative 2 is the coefficient of z, right? I'm trying to tell you why the two planes are not parallel. Okay. The first plane has a normal vector of 2, 1, negative 2, three components. Okay. The second plane, the double underlined plane, has a normal vector, let's say n2. n2, the three components of n2 are 2, negative 1, and 3. 2, negative 1, and 3, right? You see the two vectors, the two normal planes, are not in the same direction or reverse direction. Can you imagine that? A normal vector is a vector perpendicular to the plane. The two normal vectors of the two planes are not in the same or reverse direction. So because none of the vectors is a scalar multiple of the other, right? Which means these two planes are not parallel. The two planes are not parallel. When two planes in the space are not parallel, you imagine two planes in the space are not parallel. So what is the point of intersection? What is the intersection? It's not a point. You imagine when two planes are not parallel, what is the intersection? You get two pieces of papers. Two pieces of papers are not parallel. Okay. And then you imagine what is the intersection? Two planes intersect at a line, right? I'm trying to say the intersection of two planes is a line. Okay. Now in the question, I hope it makes sense. We are trying to get the equation of the line, which is the intersection of the two planes. One plane is the underlined plane. The other one is the double underlined. Okay. So we are going to get the equation, the two forms of the equations of the plane. Okay. One is the vector form. The other one is the parametric form, right? You look at the handout, okay? In handout 2, actually in handout, don't remember the number already. In handout 5, in part 6, so question 2, we have seen how to get the equation of the line if we know 2 points on the plane, right? So by that we mean for question 3, as long as we can get 2 points on the line. Again, the intersection of two planes is a line, okay? A straight line in the space. As long as we can get 2 points on the line, then we can use the method in question 2 to get the equation of the plane, either the vector equation or the parametric forms. Okay. So the first thing we do is to get 2 points on the line, 2 different points on the line. Okay. Of course, on the line you have many points, right? Now we just need 2 points on the line. Okay. To get 2 points on the line, we set x to be a particular number. Okay. Again, we are trying to get 2 points on the line. So there are many ways to do that. We set x to be a particular number, and then the two equations will become two equations of y and z, and then we can solve the system for y and z, right? So we can have 1 point, and then likewise we can get another point if we set x value or y value or z value to be some other numbers. So how about we just choose a particular x value first? You can use any x value, but use x value as simple as possible. Anybody want to give me a suggestion what x value you want to use to get a point? 0. So 0 is good. Okay. Again, I want you to imagine the intersection of two planes as a line. Okay. Now we are trying to get two different points on the line. Okay. To get two different points, we'll use a particular x value to get a point. So we use x value of 0. So to get a point, we set x value to be 0. Okay. And then the two planes will become something like this. The two equations, I mean. Okay. X value is 0. The first equation will become y minus 2z, right? Is equal to 3. And then look at the double underline. X value is 0. The second equation will become negative y and then plus 3z is equal to 6, right? Now that's a simple system with only two unknowns, y and z, and two equations. In this case, you can use any method you want. You could use the matrix method, but I see a way better method. Okay, in high school you learned two ways to solve a linear system with two equations, two unknowns. One method is called elimination. The other method is substitution, right? For this one, it's super easy to eliminate y. So anybody want to tell me how to eliminate y? I'll call that equation 1. I'll call that equation 2. How can we eliminate y? Recall what you learned in high school. Actually, we did not mention too much about how you learn the ways you learn in high school.
Addition.
Yeah, you add two equations. You add equation 1 and equation 2. You just see the coefficients of y and the coefficients of y in the two equations are opposite, right? You add two equations, you can eliminate y. So that's elimination method. Okay. So maybe equation 1, so plus 2 will yield. So now let's say you see y is gone. You just add two equations. It's permissible to do that here. You learned that in high school, right? So you have z equals 9, I believe, right? Y plus negative y is 0. Negative 2z plus 3z is equal to, I hope I did not copy anything wrong, is equal to 1. So on the left hand side you have z, right? And then you add 3 and 9. 3 and 6, I mean, okay. On the right hand side you have 9, right? So by that we mean the point is going to be a point with the x coordinate of 0 and the z coordinate of 9. We still need to figure out the y coordinate. Any point in space has 3 coordinates, right? Now I'm going to call this one 3. You can plus 3 into any of the two equations, either 1 or 2. Okay. Now we plug 3, which means z value of 9, okay, into any of the two equations. So maybe into 1. Well, let's do the thing together. Now we want the value of y. Okay. So we get y minus z value is 9, right? 2 times 9 equals 3. So which means y value equals, I don't know, 21? I think 21. Right? You move this term to the right hand side of the equation. 2 times 9 is equal to 18. 18 plus 3, I believe is 21. Okay. This argument will give you a point on the line. The line is the intersection line of the two planes. Okay. In many cases, you could have some fractions, so don't be scared if you have fractions. Actually, in this course, all the numbers are real numbers. You could have any number, right? So now we got the point on the line, right? The point with the x coordinate of 0. Originally, we set x value to be 0, okay, and the y coordinate of 21 and z coordinate of 9 is on the line. In order it's easier to communicate later, I want to give a notation for this point. So can I call this point P1? Again, we need one additional point. Okay, we need two points, so that we can use the method we used in question 2 to get the equation of the line. Now we are going to get another point. For another point, anybody want to give me a suggestion? So now let's say which x value or y value or z value you want to use to get another point. So look at the two equations. There are many ways to do that. Okay, we just need two different points. You have many points you could choose from. Okay, probably for the second point we can. Yeah, you could use x value of 1, of course. So how about if we use z value of 0? I still like zeros better than ones. It will make things easier, right? So that makes sense. We let z value to be 0. I was looking at the two equations. If you set z value to be 0, then the resulting system is simpler. It's pretty simple. So sorry, I did not. 1 will work. X value of 1 will work, but I'm going to use some different values. Okay. Probably we are going to see fractions as well. It doesn't matter. Okay, and then we have a system of two equations x and y. Okay, the first equation will become 2x plus y equals 3. I think the second equation is going to be 2x minus y, right, equals 6. I hope I did not write anything wrong. Okay, but now we have a system of two equations with two unknowns x and y. From here we can get another point. Okay, I will call this equation 3. I will call this equation 4. Okay, elimination. Now we're going to. I think it's easier either way. Okay, you add two equations, you can eliminate y. You subtract two equations, you can eliminate x. Okay, now let's get the value of x first. Okay, and so maybe 3 plus 4 will give you 3 plus 4 will give you I think 4x equals 9. Now you'll have to have some fractions. Okay, so which means x value is 9 over 4. I hope I got everything right. To get the value of y, so you could plug x value into any of the two equations. How about we subtract two equations? We subtract two equations, we can eliminate x. Okay, now we subtract two equations. So maybe 3 minus 4. You can do anything you want actually from what you learned in high school. 3 minus 4. 3 minus 4. We can eliminate x, right? So do you see 2x minus 2x is 0? And then y minus y. I think you have 2y. Equals 2y equals 3 minus 6. You have negative 3. Okay. So y value is equal to, now let's say, negative 3 over 2, right? In particular, in those cases, do not convert the numbers to decimals. I know many people in this course or in calculus still like decimals. It's better than fractions, but you convert this number to decimals, the answer is not going to be accurate, right? 3 over 2, you are going to have you have to do some rounding anyway. Okay. Now we have another point. Okay, so the point, can I call the second point P2? Okay, P2 with x coordinate of 9 over 4 and the y coordinate of negative 3 over 2 and z coordinate of z and z coordinate of 0 is another point on the line. Okay. It's on the line as well. Now we got 2 points, right? In the question, we are looking for the equation of a line. The equation has 2 forms, okay, a vector form. So can we concentrate on the vector form first? Okay. Now remember, P1 is the point 0, 21, 9. And the P2 is the point 9 over 4, negative 3 over 2. Zero, right? So did I copy this right? Hope. My memory is getting worse. I think I copied everything right. Okay, so these 2 points are points on the line, right? So we'll go from here. Now, well, that's the word. On the line. I was trying to write on the line. Okay. Now, so don't be confused, okay? You need to know what things you need to get the equation, the vector equation of the line. You need a direction vector, right? You need what? You need a point on the line. Yeah, probably you want to use P1, yeah, for the point. So because I still don't like fractions, I still try to avoid fractions in many cases. Okay. Anyway, you have 2 points on the line. You can use any of the 2 points for the equation, right? The other thing you need is a direction vector. You want to recall which vector can we take as the direction vector? We need a vector kind of on the line or in the same direction as the line or parallel to the line. I said the same thing. Okay. We can use the vector. You want to recall how to get a direction vector? You can look at your notes from last time. P1, P2 is a vector in the same direction as the line. Actually, it's on the line, right? Okay, now we can, so can I just write more word? We can take, so maybe the vector P1, P2, the vector with the initial point of P1 and terminal point of P2 as the direction vector, as a direction vector. Okay, now we have to compute P1, P2, right? P1, P2. The first component is coming from the difference between 2 x coordinates of the terminal point and the initial point. I believe it's 9 over 4, right? We'll figure out the second component soon, but we need to do some more work. The third component is simple to compute. It's coming from the difference between 2z coordinates, 0 minus 9. I think you have negative 9. We need to do a little bit more work on scratch paper to get the second component, but the second component is computed using using negative 3 over 2, the y coordinate of P2 minus the y coordinate of P1. Negative 3 over 2 minus 21. So anybody want to tell me this number in fraction? I think you can do this quicker than me. Negative 3 over 2 minus, right? To subtract two fractions, we need two fractions with a common denominator. I think you're right. Okay. Minus 42 over 2. We convert two fractions with a common denominator. Okay, that's negative 45 minus 2. Of course, you have a calculator. You can use a fraction calculator or whatever thing, or whatever way. Negative 45 over 2. Okay, so we can take that thing as a direction vector. Now we have all the information we need in order to get the equation of the line, right? We need a point. We wanted a point. We wanted a direction vector. Now we have everything. Now it's a matter of using the formula, right? So the vector equation of the line, the required line. You want to recall the form? X by z, right? Equals, I think for this one you have the point, the coordinates of the point as the components in this vector, 0, 21, 9. And then plus t is a parameter, right? T is a parameter. And then ABC are the components of the direction vector. 9 over 4, negative 45 over 2, the negative 9, right? If you don't know which one I'm talking about, I was talking about the formula on this screen, right? If you know a point on the line, if you know a direction vector, that's the vector form, that's a vector equation. You look at the mouse cursor. That's a vector equation of the line. Okay. I believe in the question we are also looking for the parametric form. Okay. Or the parametric equations. Of the line. You just compare the corresponding components, perform a vector addition in here, scalar multiplication in here. Okay. So the parametric equations of the line is x equals 0 plus 9 over 4t, right? And y equals 21 plus, actually 21 minus 45 over 2 t, and z equals 9 minus 9t. In both cases, you say something like t as a parameter. Right. Still, I want to remind you a little bit the meaning of the parametric equations. Okay. The two ways are equivalent, so all we need is to understand the meaning of the parametric equations. Parametric equations. Okay. Now let's recall I mentioned the last time, to understand the thing, all we need is to remember each value of t will give you a point on the line. Okay. T can take any real number. That's why we call it a parameter. Many values of t will determine many points. in space. Many points will form a line in this case. That's why we call it parametric equations of the line. Okay. The vector form in some cases is in some sense it's simpler, okay, and useful in some sense. Any questions about this? You're going to see a question like that on the midterm. You're given 2 points on the line, okay. No, actually you're given 2 equations of 2 planes, and then 2 planes have a point, have an intersection line, have a line of intersection. Can I say that way? Right. You are looking for the equations of the line, parametric equations of the line. Okay. Any questions? If you don't have any questions, we'll move on. Okay. I think question 4 is simple. You just need to visualize the meaning. Okay, in question 4, we are looking for, you're given a point. The point has coordinates of 1, 1, 1. X coordinate of 1, Y coordinate is 1, Z coordinate is 1 as well. Okay, and you know the line is perpendicular. The line is passing through two conditions. Okay, the line is passing through this point and perpendicular to this plane. Very quickly, anybody can imagine. Now I want you to imagine something. Okay, to imagine a point. The point is on the line. Okay, and also there's a plane. So what we are trying to get is imagine everything in 3D, right? Imagine everything in space. You have a point. The point P is here, and we are looking for the equation of the line perpendicular to the plane and passing through this point. So there's a unique line passing through this point and perpendicular to the plane. I will try to draw that a little bit more 3D. In most cases, there's a point of intersection between the line and the plane. Okay, use dotted line to denote the part you don't see. Imagine that in 3D, there's a point of intersection in here, right? We are not looking for the point of intersection. That's the next question. Okay, but now we are looking for the line, the equation of the line. Okay. To get the equation of the line, we need 2 things. We need 2 pieces of information. We need a point, a given point, right? A point on the line. The other thing we need is a direction vector, a vector in the same direction as the line. You guys are smart. Anybody want to tell me a direction vector? So just tell me 3 components. Tell me a direction vector, please. Before I give you any hint, I make any comments. Anybody want to tell me a direction vector? The line is perpendicular to the line. I'm going to use L to denote the line. I will use pi to denote the plane. Actually, that's a commonly used notation for. Yeah, 1, 2, 3 is good. 1, 2, 3 is good actually. Okay, now I'm going to tell you why it's 1, 2, 3. Okay, why it's 1, 2, 3. Okay, now you look at the plane. The plane has the equation of x plus 2y and then plus 3z, whatever on the right hand side. Okay. So do you want to recall, if you know the general form, the standard form of the equation of the plane, you can identify a normal vector. A normal vector is a vector perpendicular to the plane, right? A normal vector is a vector. Can use n to denote the normal vector. it's a normal vector is a vector perpendicular to the plane. The normal vector has three components, 1, 2, 3. So that makes sense? I told you before, right? If you know the standard form of a plane, then the vector formed by the vector with the components of coefficient of x, coefficient of y, coefficient of z, that vector is normal to the plane, right? So do you see intuitively? Yeah, that's why I told you to imagine everything in space. The normal vector of the plane is actually a direction vector of the line. The line. So because the line is perpendicular to the plane, a normal vector is parallel to the line. So that makes sense? Or on the line. So we can take the normal vector of the plane as a direction vector of the line, right? I told you why. I hope it's not too hard to understand. I told you it's important to visualize everything so that you see what's going on. Okay. The question is easy. It's easy to solve as long as you can see everything. Right. Okay, the solution. Okay. So because the line we are looking for is perpendicular to the plane. And by the way, in your solution, I'm not looking for to ask you to draw this, but you do need to visualize in order to be able to do everything properly. Okay. Since the line is perpendicular to the plane, okay, the vector. I do not have to write the equation. We have only one line and one plane. If I mention the plane, I think the plane it means that plane. Okay. So the vector n with three components, let's say 1, 2, and 3, is normal, is a direction vector, right? A direction vector of the line. Now you have a point, you have a direction vector. You are ready to get the equation of the line. Okay. If you want, we still need to use the formula on the screen. That's the vector form of the equation. That's the parametric form. Okay. So the vector form of the vector equation of the line is x, y, z equals the point 1, 1, 1, and then plus t times 1, 2, 3. Right. And the parametric form or the parametric equations of the line, you compare the corresponding components. You really only have to memorize one form, so maybe the vector form. Okay. After that, you do not have to memorize the parametric form. Compare the components. It's easy to get the parametric form. Okay. So you have x equals, I think, 1 plus t, and then y equals 1 plus 2t. It's pretty yeah, it's very nice numbers. Z equals 1 plus 3t, right? Say something like where t is a parameter. Okay. Any questions? You see, it's kind of important to visualize what's going on here. Visualize the line, visualize the point, visualize the plane. That's question number 4. Okay, now we're doing the next question. Okay, part 7. On the midterm, you are going to see a question like that. You are given an equation of a line. You are given an equation of a plane. Okay, the line is not parallel to the plane, so the line and the plane has an intersection. I will try to show you what I mean. Okay. I do not want to make the things too complicated, but in the question you have the equation of a plane. You look at the mouse cursor, okay? The equation of a plane, and parametric equations of a line, right? So that's the parametric form of the equation of a line. I do not want to make the things too complicated, but it's easy to see. It's possible to see the line is not parallel to the plane. I will try to still draw something, okay? You have a plane. The plane has the equation x plus y plus z is equal to 9. And you have a line. I told you the line is not parallel to the plane. So does it make sense? If the line is not parallel to the plane, they have a point of intersection. The line intersects the plane at only one point, right? That is a point of intersection. Now can I call this point P? Now I'm looking for the coordinates of this point. So does that make sense? So the question is asking, and by the way, the line is not perpendicular to the plane. It does not have to be perpendicular, right? As long as the line is not parallel to the plane, they have a point of intersection. They have one and only one point of intersection. Now we are looking for the point. Okay. We are looking for 3 numbers. We are looking to tell me a point. You have to tell me 3 numbers. What is the x coordinate? What is y coordinate? What is the z coordinate? Right. Yeah, probably the only thing you need to recall is each value of t, each value of the parameter will determine a point. The point has to be a point on the plane, right? The point is a point on the plane. There must be a value of t to determine that point. Now, how can we get the value of t? Can anybody try to write something down or tell me something? A description, how can we get t? We plug x value of t, y value of t. We plug x in terms of t, y in terms of t, z in terms of t in the equations of the line into the equation of the plane. You are going to have an equation of t. We solve the equation for t, okay? And then we can get the point. I will show you what I mean. Okay. Now the solution. I will try to write some wording to let you see what's going on. Okay. We plug x equals, let's say 1 plus t, y equals 1 plus 2t, and z equals 1 plus 3t. I think that's the line we just found in here. Exactly the same line as the line in question 4. You see that? Into the equation of the plane. I mean into the equation of the plane. So now let's say x plus y and plus z equals 9. So what are we going to get? I told you we are going to get an equation of t. One equation of t. We are going to get, now let's say, you replace x with 1 plus t. This x is that x, right? 1 plus t. And then 2 plus t. 1 plus 2t, I mean. Sorry. To make you see what's going on, I'm going to use some brackets. It's not necessary to use brackets, okay? But I want you to see that is x, okay? And then we replace y with 1 plus 2t. We replace z with 1 plus 3t, right? 1 plus 3t, I think I got that right. Equals, on the right hand side you have 9, right? So you have, that's why I said you have an equation of t. You solve the equation for t, you have a value of t. That value of t will determine a point on the line, right? That line is, that point is on the line and also on the plane. That's the point of intersection. You got the idea? Okay, now let's simplify a little bit. Okay, how many t's altogether? I think altogether you have 6 t's, right? 1t, 2t, 3t. You have 6 t's, and the number part I believe is 3. 3 plus 6t is equal to 9. So you have 6t equals 6, right? So which means t value is equal to 1. Actually, I was trying to make some nicer numbers. So t value is 1. Okay. Now t value of 1 will determine a point. That point is going to be on the line and on the plane. By that we mean that is the point of intersection of the line and the plane, right? So okay, and the point of intersection of the line and the plane is the point with x coordinate. And so maybe I'm running a little bit faster for some of you guys. It's the point when t value is 1, you plug 1 into here. Now look at the cursor. I think x coordinate is 2, right? And y coordinate, anybody want to tell me the y coordinate? 5. Sorry, it's not 5. It's 3. T value is 1. Sorry, it's 3. And the z coordinate of the point is 4, right? You just look at here. So z is 1 plus 3t. T value is 1, right? 1 plus 3 is 4. That's how we get a point of intersection. Again, on the midterm, you are going to see a question like I'm asking you for the equation of a plane. So I'm going to make more comments. So okay, but a question like that is going to be on the midterm. I'm going to make some comments. So okay. Any questions about this? Simple, right? Again, the most important thing is to visualize, to see what's going on. As long as you see what's going on, the numbers are simple. The calculation should not be too hard. Okay, but you do need to know what's going on, right? I think we have one more question left on the handout. A question like this. I'm not 100% sure if I want to include a question like that on the midterm or not, but I want to go over this. a question like that is going to be on the quiz if you have a quiz. So we'll see. I haven't decided. I will try to make some comments on midterm first. Okay. If I'm happy, I'm ready to go, and then I will give you a quiz. I will let you know before the class. Okay. Anyway, we're going to do this question first. Okay. It's a proof. Question in the nature of proof. Now you look at the question. You're given two vectors u and v. Actually, the two vectors can be in any Rn. To make it simpler, you just imagine u and v are two vectors in R3. It's okay. It's going to be the same thing. Okay. What I want you to prove is these two vectors are perpendicular. Okay, orthogonal. Okay, I will show you the proof. I think you have thought about this for a little while. Okay. For two vectors, how can we prove two vectors are perpendicular? Anybody want to tell me something? How to prove two vectors are perpendicular? You are not given a whole lot of information. You just know two vectors are unit vectors. You know the length of the two vectors are 1, right? Then how can we prove two vectors are perpendicular?
Dot product is 0.
Yeah, the dot product is 0. We compute the dot product, right? As long as we can use the conditions to confirm yourself the dot product is 0, and then you are ready to go. Okay, so before doing that, I will show you some conclusions we need to use. I think it's still in this chapter. Okay. The dot product, right? The dot product, we want to convince ourselves the dot product is equal to 0. Actually, the properties I was trying to recall are some properties in here. Probably I forgot to mention something in class. I was too eager to jump to the calculation stuff. But, okay. I will make some comments. Okay, now let's look at some properties of the dot product. Okay, to make this simpler, we imagine two vectors in R2. Okay, so now let's say u is the vector. So now let's say 1, 2, and the v is a vector. So now let's say 3, 4. We defined the dot product before, right? The dot product, you have to use a notation like u dot v to denote the dot product. The answer to a dot product is a number. Now let's recall how we compute the dot product. It's 1 times 3, right? And then plus 2 times 4. You multiply the corresponding components of the two vectors, and then you add the products. So you have the dot product. In this particular case, the answer is a number. Okay. Right. Now, after that, I want you to know some properties. The first property is the dot product is commutative. I believe you can see it doesn't matter you compute the u dot v or v dot u. The answer, they should be the same. Okay, it's commutative. The second property is it's kind of the dot product is distributive over addition. You do not have to write the name. You just remember we have a property like that. Okay. The third property is kind of associativity. You have a scalar multiple. scalar multiplication as a dot product in here. I was trying to say the three forms are equal. So do you see you have kind of associativity? You group them in different ways. The answer is the same. Okay. Actually, formula number 4 is kind of important. I'm sure I forgot to mention that in class. Okay, I will make that up right now. Okay. Now let's say for a general vector. So this time I use u to denote the vector with two components a, b. We only talk about the vector in R2. We only talk about that case. Okay. Now I want you to see the identity. I'm talking about property number 4. Okay. Now let's compute the. Now let's verify the identity. Okay. Now let's compute u dot u. So what's u dot u? U dot u is you compute the dot product of u and u. I believe you use the formula. You have something like a squared and plus b squared. So do you see it? You multiply the corresponding components. You add the products. You have a squared and plus b squared. That's u dot u. I'm pretty sure you can recall how we compute the length. The length of u is computed using square root of a squared and then plus b squared, right? So does that make sense? The length of u, the whole thing squared, is a squared and then plus b squared, which means u dot u, the dot product of u and itself, is equal to the length of u, the whole thing squared. Alternatively, you can try to understand that as the length of u can be computed in terms of the dot product as square root of u dot u. You see, everything is true when u is a vector in R2. So that's a vector in R2, right? When u has two components. Actually, the same conclusion is true for any vector in Rn. Okay. Actually, in the proof, we are going to use property number 2 and property number 4. We'll go back to the proof. Okay. Try to remember the properties. Okay, now the proof. When I want you to prove something, you do not write solution, you write proof. You know that in high school, right? You write proof. Now we are trying to compute the dot product of two vectors. So either way, however you want, whichever you want to do it first or second. Okay. Okay. Now I want to compute the dot product of u plus v, and you have to write dot in here. Okay. And u minus v. Actually, it's kind of okay. I will try to let you see the geometric meaning very shortly. Okay. You treat the underlined vector as a whole. You treat the underlined vector as a whole. Okay. You just imagine that's a vector w. Okay. And then we apply the distributivity. Actually, you can imagine if I replace the plus sign with a minus sign, the property is also true. Okay. It's kind of you distribute the whole underlined vector into these two terms. Okay. It's comparable to number multiplication and stuff and addition, but they're not quite the same thing. So, but the property says this one is equal to u plus v, right? dot u, and then minus u plus v, then dot v. Okay. All right. We did nothing but using one of the properties, the distributivity. Now suppose you want, I can change the order a little bit, but it's commutative. It doesn't matter you change the order or not. I'm trying to say I'm going to give you the proof in some more details. Okay. You know what I'm doing? I was switching the two factors. You see they're equal, right? Now for instance, you look at that term, okay? I switched the location of the two factors, commutativity, using the commutativity. Okay, now the next step we are going to use the distributivity again. Okay. So you have something like u dot u, and then plus u dot v. So do you see what's going on? Now you look at the brackets. Okay, minus. I will put all the stuff inside brackets. Okay, v dot u, and then plus v dot v. Originally, we wanted to prove the dot product is equal to 0. At this point, you are not quite C0 yet, but we are close. We are very close already. Okay, it's kind of so don't be confused. Every term now is a number, right? You have 4 numbers. That number plus that number minus that number and then plus that number. Can you recall the dot product of two vectors as a number, right? So you have u dot u, right? Now we are going to get rid of the brackets, and then plus u dot v, then minus. In this step, I'm going to use the commutativity. U dot v is the same thing as v dot u. Okay. I will write that term as v dot u, as u dot v. Okay. And then minus. Again, every term is a number. You get rid of the brackets. You have to turn the sign, right? Minus v dot v. So do you see the two middle terms are cancelled, right? So they are the same thing. They are the same two numbers. So you end up with. Now I'm going to use the other property I mentioned. U dot of u can be written in terms of the length of u as the length of u, the whole thing squared, minus v dot v can be written as the length of v, the whole thing squared. So what is that? So do you have 0? Now look at the condition. You have two unit vectors. We mentioned before a unit vector is a vector with the length of 1. So the length of u is 1, the length of v is 1, right? So you just have 1 minus 1, so which is 0. Now you look at two sides of the equation, okay? The two sides of the equation. On the far left, you have the dot product. We have proved the dot product is equal to 0. That's why the two vectors are perpendicular, right? Are perpendicular, are orthogonal. Actually, you can kind of see what's going on. You just try to draw two vectors of the same length. Okay, So now let's say U is here, V is here. So do you want to recall where, okay, U and V are the same length? Sorry. Okay, I'm going to redo it. Okay. So now let's say U is here. Now let's say V is here. Wherever they are, as long as they have the same length, the argument will be true. Okay. So do you want to recall where how can we determine U plus V? You need to draw a parallelogram, right? Yeah, something like that. That is the vector U plus V using the parallelogram rule. So that's the vector of U plus V. Okay. So do you want to recall where U minus V is? Where U minus V is? U minus V is here. They are perpendicular. Okay. As long as U and V have the same length, intuitively you can see they're perpendicular.